So we're going to talk about mixtures of gases. Many gas samples are mixtures rather than one single pure gas. One of the gases that's most important to us is air, and air is a mixture of several gases. This is the composition of what's called dry air. Wet air would be air with humidity, right? So it has water vapor in it. So if you get the water vapor out, dry air would be 78% by volume nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide. And then do you think there's maybe some other things in the air as well? Sure there are. I know when my teenage boys eat too much chili, there's definitely other gases in the air, right? Smelly ones. But all those other gases are very, very small quantities, smaller than the amount of carbon dioxide. So we can characterize a gas by looking at the percent composition by volume. So 78% means that if you had, let's say, 100 liters of air, 78 of those liters would be nitrogen. So we've talked about percent by mass. This is percent by volume, where you're just measuring the quantities using volume instead of mass. In some applications, we can treat a gas mixture as a single gas. We can measure the pressure, the volume, the temperature of air, and treat it like it was one substance. We can even calculate the number of atoms/molecules in that sample of air. And that's because gases behave independently of each other. So gas particles don't interact with each other, and there's so much empty space between them that the size of the individual molecules doesn't matter. And so it doesn't actually matter which gas it is. We can calculate pressure, volume, temperature. So the pressure of a single gas in a mixture is called its partial pressure. This is a little bit like if you had a box of fruit, right? And you had apples, and you had oranges, and you had bananas. There's a total mass of fruit, right? Maybe it weighs 10 pounds. Each fruit is contributing mass to the overall mass of the fruit. So there's a mass of apples, a mass of oranges, a mass of bananas. The mass of the bananas doesn't depend on the mass of the apples or the oranges. It just is what it is, right? And they all contribute to the total mass. It's the same idea with pressures of gases. So each gas contributes a pressure to the total pressure. And to distinguish that from total pressure, we call that partial pressure. So the partial pressure due to a single gas, and here we'll just call it P sub n, can be calculated from the ideal gas law. So the pressure of gas N would equal the number of moles of that gas times RT over V. Just a rearrangement of the ideal gas law, right? John Dalton worked with gas mixtures, and from his work we have what's called Dalton's law of partial pressures. The sum of the partial pressures of all the gases in a mixture equals the total pressure. So that can be expressed mathematically. This way P total is the pressure from partial pressure from A plus the partial pressure from B, etc. However many gases are in there. Just like the mass of the fruit. Okay? So the total pressure equals the partial pressure from each component. The partial pressure of gas A could be expressed as the moles of gas A times RT over V. And the partial pressure of B is the moles of B times RT over V. All of these gases are in the same container. They have the same temperature. They have the same volume. Okay? So RT over V is the same for each of these. So we can factor that out. We can factor the RT over V out. And then we've got moles of A plus moles of B plus moles of C, and we could call that total moles of gas. So the total pressure of the gas sample equals P total equals the total number of moles of gas times RT over V. So what if we take the expression for the partial pressure of gas A, so that equals the moles of A times RT over V. We divide that by the total pressure, which is equal to the total moles of gas times RT over V. RT over V doesn't change, and so those variables cancel out. And we end up with the partial pressure of A over the total pressure of A equals the moles of A over the total moles of gas. So if a gas is 25% in terms of numbers of moles of the entire sample, it's going to exert 25% of the pressure. Kind of makes sense. This term here is called a mole fraction. It's like a percentage, except we didn't multiply by 100. It's the part, moles of gas A, divided by the total moles. The part over the whole, but we're just skipping the times 100 part. Call that mole fraction, and that's given the symbol chi. It's a capital chi, Greek letter. So chi sub A is the mole fraction of A. So that's the moles of A divided by the total moles of gas. So here we have this equation rewritten down here. We can solve that for the partial pressure of A. So that's equal to NA over N total times P total. And this guy right here is chi. So we end up with this expression down here. The partial pressure of a gas in a mixture is equal to its mole fraction times the total pressure. So, like I said, if it was 25%, well, if it's 25% of the total, then the mole fraction is 0.25. Okay? So you don't have to know how to derive all of that, but you should be able to use this equation down here. So the partial pressure of a gas, a component of a gas mixture, is its mole fraction multiplied by the total pressure. Because volume of gas is directly proportional to number of moles of gas, the mole fraction of a component is the same as its percent volume divided by 100%. So the volume fraction and the mole fraction end up being equal for gases. So from an earlier table, we know that nitrogen makes up 78% by volume of air. Yeah, I noticed this yesterday and I forgot to fix this. Air has, this still isn't very good, but it's a better sentence. Air has a 78% composition of nitrogen. Air is 78% nitrogen. I don't know where that's a mess. Find the partial pressure. Well, so here in this room, the pressure is about 1 atmosphere. So the total pressure is 1 atmosphere. So what I'm doing here, the partial pressure of nitrogen is going to equal its mole fraction times the total pressure. The mole fraction of N2 equals the percentage of N2 by volume divided by 100. So the fraction here is just the percent without the times 100. So if nitrogen is 78% of the air, then it has a pressure of 0.78 atmospheres. So there's a lot of problems that we can pose. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. Because what if you have something that reacts with air? How do you keep that from reacting, right? Air is everywhere. Well, you can either put it in something like an oil that'll keep the air out, or you can put it in a container and replace all the air in the container with something inert, like noble gases. So that's what's going on here. So a chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. Now this is not a simple problem. The idea is simple, but then the actual solving of it gets rather tedious. We have to be able to read a problem like this and figure out what all those words are saying, right? And a lot of this, like this first sentence, that's all just like background. Do we need to know it's a chemical engineer? No. We need to know that we've got these three gases, and we need to know STP, and then we're calculating this. So maybe we could do this. This I'm going to highlight, and then we're supposed to calculate the partial pressure. The rest of the words, really, we don't need those. So we have a mixture of gases, and we want to know the partial pressure of each gas. So then we have to start thinking, well, what relationships do I know? So up here at the top, we know that the total pressure, I'm just going to do P total, that's not a very good capital T. I'm just going to do PT because I get tired of writing the word total in little tiny letters. The total pressure for this mixture is going to equal the pressure of each individual gas added together. That's what Dalton's law of partial pressure says. So that would be the partial pressure from the helium plus the partial pressure from the neon plus the partial pressure from the krypton. Well, that's true. Do we know any of those pressures? What do these three letters tell us? Standard temperature and pressure. So that tells me that the total pressure equals what? 1 atmosphere. And what's the temperature? 273 Kelvin, or 0 degrees Celsius. So we know the total pressure, but that doesn't help us here because there's three things, and you can only solve for one variable. What else do we know about the relationship between a partial pressure of a gas and the total pressure? It involves that funny Greek X, chi. The partial pressure of, I meant to write helium. The partial pressure of helium is equal to the mole fraction of helium times the total pressure. The partial pressure of neon equals the mole fraction of neon times the total pressure. The partial pressure of krypton equals the mole fraction of krypton times the total pressure. So we know the total pressure. The partial pressure is what we're trying to find. Could we calculate the mole fraction? Yeah, we could. So mole fraction for helium equals the moles of helium divided by the total moles. Did they give us moles of helium? No, that would be too nice. They gave us a mass of helium. Could we figure out the moles of helium? Yeah, we could. So let's do that. 5.50 grams of helium. So 1 mole per 4.003 grams. Molar mass of helium from the periodic table. So I'm going to keep track of my significant figures and not round things yet. So that's the moles of helium. And then we'll do the same thing for neon. So 15 grams of neon 1 mole over 20.18 grams. Zero 0.743 31 moles. And then the same thing for the krypton. What? $35 grams of krypton times 1 mole over 83.80. .41766. So that's my moles of krypton. So what I need here is the mole fraction. So for the mole fraction for helium is equal to the moles of helium, 1.3739 moles, divided by the total number of moles. So the total number of moles, I have to add all three of these together. So 1.3739 plus 0.74331 plus 0.41766 equals, so forgot what I was doing. Total number of moles is the moles of helium plus the moles of neon plus the moles of krypton, which is 2.53487 moles. So if I'm thinking about significant figures when I add these, this number has 2 decimal places in terms of significant figures. This one has 3 and this one has 3. So my last sig fig in that sum would be the second decimal place. So what happens to the mole units when I do this? They cancel out. The fraction has no units. So 1.3739 divided by 2.53487 equals, so this mole fraction, I'm trying to color code here to make it a little clearer. So that's the mole fraction of helium. The partial pressure of helium equals the mole fraction times the total pressure. What's the total pressure? 1 atmosphere. So I'm going to write this out once, but I'm not going to write the others out. So the partial pressure of helium equals this 0.54200 times the total pressure, which is 1 atmosphere. Multiplying by 1 doesn't change anything. So the pressure of helium equals 0.542 atmospheres. Okay with that? I needed to find the mole fraction and then multiply by the total pressure. Since the total pressure was 1 atmosphere, that math is pretty easy. At 1 atmosphere, the partial pressure ends up equaling the mole fraction. So then things just get tedious, or maybe I should say more tedious. because we have to do the same thing for these others. I'll do it this way. So the mole fraction of neon equals the moles of neon, 74331 moles, divided by that same 2.53487 moles. That's the total number of moles. So this equals 0.29323. That's the mole fraction. And then if we multiply by 1 atmosphere to get the pressure, we get 0.293 atmospheres for the neon. Make sense? So krypton, we could get its mole fraction 2 different ways. We can do this same thing, or we can recognize that all the mole fractions have to add up to 1, right? So it just kind of depends on what seems easier to you. Since there's 3 things here, I'd have to do 1 minus this, and that seems to be a little more work than just doing the division. So I'm just going to do the division. The mole fraction of krypton is the 0.41766 moles, divided again by that 2.53487 moles. Decimal point didn't show up very well. Moles cancel out. 0.16476 is my mole fraction. When I multiply that by the total pressure of 1 atmosphere, I get 0.165 atmospheres. What do those partial pressures have to add up to? 1, the total pressure. And if you do that, they do add up. I checked that yesterday. Any questions? Let's do another one. A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What is the amount in moles of hydrogen gas in 1.55 liters of this mixture at 298 K? Well, there's lots of numbers in here. So a good strategy would be to pull the numbers out and identify them. So I've got 755 torr, just the 2 R's, that's enough. And then I've got 24 torr. So those are both pressures, right? But now we know there's different kinds of pressures, right? So 755 torr, it says that's the total pressure. So I'm going to call that P sub T for total pressure. The water vapor is another word for gas. So water in the gas state has a partial pressure of 24. So I'm going to call that PH2O. And then we've got 1.55 liters. That would be a volume, right? And we've got 298 K. What's that? Temperature. The words in the problem don't tell us that, but we should know that liter is a unit of volume, Kelvin is a unit of temperature. So we use the unit to identify what those numbers are. And then what are they asking us to find? Moles of hydrogen. So moles of hydrogen equals what? Question mark. Well, if I just gave you this volume and this temperature, how would you find the gas? You'd need the pressure, right? And then we're going to use the ideal gas law. So we know the ideal gas law, PV equals nRT. If we want the moles of gas, N equals PV over RT. So we're trying to find N. We need pressure, volume, and temperature, and then we've always got the gas constant. If we want moles of hydrogen, we need the pressure of just the hydrogen. If we use the total pressure, we're going to find the total number of gas particles, and that's not what we're interested in. We don't care about the water, we just care about the hydrogen. So how do we figure out what the partial pressure of the hydrogen gas is? Dalton's law of partial pressures tells me that the total pressure equals the sum of the partial pressures. So that's the pressure of the hydrogen plus the pressure of the water. So if I want to know what this one is, I'm going to take the total pressure and subtract the pressure of the water. So let's just subtract, and we've got 731 torr. I did that in my head, just, subtracting there on the paper. And that's fine. You can do that. But on something that's being graded, check it with a calculator. I see a lot of stuff where people stack it like this, and I can tell there's cross-outs and you borrowed and subtracted and stuff, and you got the wrong answer. That's dumb. Poor, long subtraction skills should not give a wrong answer when you got all the complicated chemistry stuff right. So just use the calculator. This is the pressure that we need to use. Well, we always have to think about units, right? So what units do we need on these things? How do we know what units we need on these things? Come on, it's almost 8:35. You should be awake by now. What's the ideal gas constant? It's 0.08206 with those crazy units. Liter, atmospheres, per mole, Kelvin. These are the units I need. It's easier if you switch the units before you stick them into the equation. So my temperature's in Kelvin. That's awesome. My volume is in liters. That's great. My pressure is in torr. That's not okay. So we have to convert that. All pressure conversions can be done in one step because the table of pressure conversions, all of those things equal 1 atmosphere. So you can pick whichever 2 units you need, stick them in a fraction, and be done with it. So I want torr on the bottom, and I want atmospheres on the top. This is one you should memorize. 1 atmosphere is exactly equal to 760 torr. The reason you should memorize it is because we use it all the time. And it's tedious if you have to keep looking it up. So this is 0.96184 atmospheres. Again, don't round off too much. You can use the whole stinking number if you want to, although I find that really tedious. I've been using the word tedious a lot. Life has seemed a bit tedious to me lately. I'll maybe work up. It just sounds fancier than boring. Because, I'm always on my kids about saying boring. Well, if you're bored, that means you're a boring person, right? Okay, we've got our values here. Let's just finish this off here. So N equals PV over RT. So the pressure we just figured out was 0.96184 atmospheres. The volume, 1.55 liters. Divided by R. 0.08206 liter atmospheres per mole Kelvin, and the temperature 298 Kelvin. Checking the units, atmospheres cancel, liters cancel, kelvins cancel. I'm left with moles. So I've got the pressure, which is still sitting in my calculator, times 1.55 divided by 0.08206 divided by 298. Again, make sure that you're communicating correctly with your calculator. So I'm getting 0.0610 moles of hydrogen. If you're getting a much bigger number, it means you're accidentally multiplying by 298 instead of dividing by it. Any questions? Yeah.
In the calculator, it's also got PA. Is that pressure?
So it has a PA as a button?
No. It's got a respector in it, but
I have no idea. Yeah, I'd be happy to look at it, but off the top of my head, I don't know what PA means on your... I mean, it could be atmospheric pressure, but I don't know. I'd have to look at it. Yeah. Yes?
Can you explain why you subtracted 24?
Yeah, I subtracted 24 from the 755. Okay, so we have a mixture of gases here. The total pressure is 755. And the pressure of the water is 24. I'm looking for moles of hydrogen, and so I need the partial pressure of just the hydrogen. That's a good question. Anybody else? Deep sea diving. So a deep sea diver dives deep into the sea. Sorry, I don't know. I never know what to say about this one. So you go deep under the water, you need to breathe, right? And so you need air. And so you take it in a cylinder on your back, compressed air. It needs to be under pressure because, as we discussed earlier, the farther under the water you go, the more pressure the water puts on you. And if the air you're breathing isn't pressurized, your muscles aren't strong enough to expand your lungs against the pressure of the water. So you're breathing pressurized air, compressed air. Well, if the total pressure of the air that you're breathing goes up, what happens to the partial pressure of oxygen? It also goes up. Because the composition of the air is the same. The mole fraction of oxygen in that air is the same as it is at the surface if it's just compressed air. If the total pressure is larger, mole fraction times total pressure is going to give you higher partial pressure. So one thing I would like you to come out of this class really grasping is that anything is toxic at levels that are too high. We need water for life, right? You can't live without water, but if you drink too much water, you will die. And if there's too much water in your environment because it's flooded and you don't know how to swim, you're also going to die from too much water on the outside, right? Too much oxygen can kill you too. But then too little oxygen will kill you. There's this sweet spot in the middle. So we tend to think of chemicals as being bad and dangerous when actually your body is made out of chemicals and everything we need to sustain life is chemicals. So really it's not that there are bad chemicals or good chemicals, it's the amount of them. So oxygen toxicity is going to happen at high partial pressures of oxygen. Hypoxia happens at low pressures. And there's that prefix hypo again. Hypo means below. Hypoxia means low oxygen. If you don't get enough oxygen, you're going to die. So oxygen, when would the oxygen pressure be too low? Well, if you went to a very high elevation. As you go higher up in the mountains, or even worse, if you go up in an airplane that doesn't have a pressurized cabin, atmospheric pressure is lower, lower total pressure, lower pressure of oxygen. You do not need to know the values in this table, but this is just to give you an idea of safe ranges. So we want a partial pressure of 0.21. That's like our sweet spot for oxygen. And that's what we've got at sea level, and we're all comfortable here. Now, you can become accustomed to slightly lower levels, but if you go much lower, down to 0.1, you get into hypoxia and you're going to be in trouble. Have you heard of elevation sickness? Some people are more susceptible to that than others, but you go to somewhere that has a high elevation, there's not as much oxygen, and some people's bodies react very badly to that and they can get really, really sick. The treatment is to go lower, get more oxygen by going to a higher atmospheric pressure. If you're breathing 100% oxygen at the surface, that's still within the safe range. If you're exerting yourself, you can be getting, okay, yeah, I guess. So at a higher pressure of gas that you're breathing, if you're exerting yourself, then your body can handle more oxygen. But the maximum you can handle at rest is a partial pressure of 1.6. Above that, it's just really bad for you. Now, the good news is that you're not accidentally going to poison yourself with oxygen, right? You kind of have to do that intentionally. So if we're breathing compressed air, that increases the partial pressure of oxygen. It also increases the partial pressure of nitrogen. And so at the surface, where the total pressure is 1 atmosphere, we've got a partial pressure of nitrogen is 0.78 atmospheres. 30 meters below the surface, you need a total pressure of 4 atmospheres. Now your nitrogen partial pressure has gone up to 3.12 atmospheres. Oxygen's gone up to 0.84. That's still okay. When you get, so here you have 3.12 atmospheres. You get up above 4 atmospheres of nitrogen partial pressure, and that starts to become a problem as well. It's called nitrogen narcosis, or rapture of the deep. It's similar to being intoxicated with alcohol. So you might say, well, we do that for fun on the weekends. Yeah, but if you're 30, 40, 50 meters below the surface of the water, you don't want your judgment to be impaired, because getting confused about which way is up could lead to your death, right? So not real safe. And the book doesn't really go over it, but this increased nitrogen pressure is also what causes a condition called the bends. So if you come up from deep submersion too quickly, the oxygen is in your blood, the nitrogen is also in your blood, and if you come up too quickly, the nitrogen actually bubbles out of your blood, causing a lot of pain, and it can kill you. And so that's why they advise that you rise slowly so that the nitrogen has a chance to come out of your blood. There's all this chemistry in deep sea diving. There's a reason they make you take all those classes and get certified. It's a lot more complicated than it seems. Pardon me?
Sit in the chamber for months.
Yeah. So if too much oxygen's bad, what do? We can't breathe compressed air at a real high pressure. So we breathe compressed something else. So one thing that they use is called heliox. So it's a mixture of helium and oxygen. Helium makes your voice high and squeaky, but it really doesn't do anything else to you. So you cut the oxygen with helium, basically. So then you need 2 tanks. You need the compressed air and you need the heliox. And as you go deeper, you gradually switch from one to the other, and that way you can maintain a good oxygen level. So that's all just like background, hopefully somewhat interesting stuff. Anyway, diver breathes. Okay, start over. A diver breathes a heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? Okay, well, let's pull the numbers out and see what they are. So we've got 0.050. It says that's the mole fraction of oxygen. So the letter we use for that is this capital chi, the funky X. So the mole fraction of oxygen. And then 0.21 atmospheres. That's the desired partial pressure of oxygen. So we call that PO2. And what are they asking us to find? Total pressure. What must the total pressure be? Well, in all those equations we've talked about, is there an equation that has these three variables in it? Yeah, there is. The partial pressure of a gas is equal to the mole fraction of the gas times the total pressure. So if I want the partial pressure, I'm just going to divide by the mole fraction on both sides. The total pressure equals the partial pressure divided by the mole fraction. So total pressure is, partial pressure is 0.21 atmospheres. Divide by 0.050, the mole fraction. 4.2. Bless you. So with this heliox mixture, you need the total pressure to be 4.2 atmospheres, and then you're getting a good amount of oxygen. Any questions? So we've done experiments that generated gases. One I can think of is the copper. We took the copper wire, we added nitric acid in the hood, and we saw this brown gas, right? And where did the gas go? Did we put it in a beaker? No, it went into the air, right? And that's why we did it in the hood, so that it could be vented, right? Because it's not safe to breathe that. Well, sometimes we collect the gas. How would you do that? Here, gassy, gassy. Come over here. No, it's hard to collect the gas, right? Gases are kind of squirrely that way. They just float away. So we do that by displacing water from a container. So I'm going to skip ahead and look at this. So this is an illustration of one way you can collect a gas. We call it collecting a gas over water. So this setup here looks a lot like that mercury barometer picture. So here we've got this container. It was originally full of water, and we have it inverted in a dish of water. Over here in a test tube, we have our chemical reaction that's generating hydrogen gas. We're allowing the hydrogen gas to leave through a hole in this stopper, and we're channeling it through this tubing, and we're letting it go under the inverted container here. So the gas will float up and get trapped up here. As it goes up there, it's going to displace the water. Does that make sense? So up here, we're going to have the hydrogen gas that we're collecting from the reaction, but we're also going to have water vapor because the water is evaporating. And we'll talk more about that, how that happens. But for now, just it's enough to know that water evaporates. And so we're going to have water vapor in here along with our hydrogen. So we're going to have a mixture of two gases. This is called a wet gas because it has water in it. So if we want to know the pressure of the hydrogen gas that we're trying to collect, we need to know what the pressure of the water vapor is so we can subtract it from the total pressure. Very conveniently, the partial pressure of the water vapor, which we call the vapor pressure, depends only on the temperature. Higher temperature, higher vapor pressure. Lower temperature, lower vapor pressure. And so we just look it up in a table and we know what it is. It's not anything we have to measure because somebody else has done the hard work of measuring and tabulating it. There's not a real convenient equation for it, but these tables can be found all over the place. This one isn't very detailed. It just goes every 5 degrees Celsius. We see the pressure of the water, the vapor pressure of the water increases until at the boiling point it's equal to atmospheric pressure. In this table, the pressure is given in millimeters of mercury. So you just have to pay attention what's the unit that's being given. Okay, a sample of acetylene is collected over water. The total gas pressure is 738 torr, and the volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? Well, there's another problem with a whole bunch of words and a bunch of numbers. Pull the numbers out, write them down. 438 torr. So how should I label that? Total gas pressure is, right? Come on, guys, wake up. That's P total. See, I was trying to trick you. No, I'm an idiot, that's all. I'm not an idiot, I just do dumb things sometimes. Okay, thank you for that. I don't know where I got a 4 from. There's not a 4 anywhere on this page even. 2 plus 2 is 4. Okay, 523 milliliters. Something equals 523 milliliters. What's that? Volume? Then they're saying 23 degrees Celsius. Well, that would be the temperature, right? And then we have the vapor pressure of water is 21 torr. So the vapor pressure of water means the same thing as the partial pressure. So that's the partial pressure of water. We have 2 gases in this mixture. The total pressure equals the pressure of, this isn't hydrogen this time, the acetylene plus the partial pressure of the water vapor. So we need to subtract the mass of the water from the total pressure to get the pressure of the acetylene. You guys okay with that? So they're asking us for grams of acetylene. Well, what does the ideal gas law allow us to calculate? Does it give us grams? Does it? Is mass in grams part of the ideal gas law? Remember the ideal? No, thank you. PV equals nRT. N is moles. There's nothing with grams in there. But if we knew the moles, could we find the grams? Sure we could. So what we're doing here is we're taking different pieces that we've learned separately and we're putting them together. So we're doing a Dalton's law of partial pressures problem to find the partial pressure of the acetylene. We're going to do an ideal gas calculation to find the moles of acetylene. Then we're going to use the molar mass to find the mass of acetylene. There are so many different ways that these little pieces can be put together. I can't possibly show you an example of each thing you might encounter. And even if I did, there's no way you could remember all of them. So this is, again, where critical thinking comes in. You learn the individual pieces, and then what's really different about 1A is that you have to be able to put those together yourself. Okay, so we want to find the moles of acetylene. That's PV over RT. Before you plug these numbers in, check them to see that the units are okay. Are those units okay? No. We're comparing them to the units in the ideal gas constant, liter atmospheres per mole Kelvin. None of them are good. So we have some converting to do. So 717 torr. Well, 1 atmosphere is 760 torr. So we take that one and divide by 760 to get atmospheres. 0.94342 atmospheres. That's our pressure. 523 milliliters. So milliliters to liters is a 3 decimal place moving of the decimal point. Milliliter is a small unit, liter is a big unit. We should all be aware of that. So if I'm going from a small unit to a big unit, the number has to get smaller. And so this is going to be 0.523 milliliters. It's not going to be 523,000, liters. 0.523 liters. It's not 523,000 liters. Just think about bottles of soda, right? Over 2,000 bottles of soda is 500 milliliters. That doesn't make any sense. If you tend to do it the wrong way, write the whole thing out with the times 10 to the negative third and do all of that. 23 degrees Celsius, we're going to convert this to Kelvin by adding 273. We get 296 Kelvin. So now we've got things with correct units. Yes?
You said that it's Kelvins, liters, and
Atmospheres
that are all...
that we use in the ideal gas equation because of the ideal gas constant that we're using, 0.08206 liter atmospheres per mole Kelvin. Yeah. Now, there are a lot of times where we take a combination of units like that gets used all the time, and we give it a new name. Okay? We don't want to do that here because we're going to be using these other units and we want to be able to see how they cancel out. So that's why it's just got this messy units. They're actually helpful because they tell you what units you need on your other quantities. 0.94342 atmospheres. That's my pressure. Pressure times volume divided by ideal gas constant, 0.08206 liter atmospheres per mole Kelvin times the temperature, 296 Kelvin. Checking the units, atmospheres, liters, Kelvin. You know, if you have a brain fart and you forget this equation, you could figure it out from the units in R. 0.94342 times 0.523 divided by 0.08206 divided by 296. 0.020313 moles of acetylene, C2H2. We're not done yet, though. We need to convert moles to grams. So we need a molar mass, 2 times the mass of carbon, plus 2 times the mass of hydrogen, (23.036). grams per mole. Point 0.020313 moles. Grams on top, moles on the bottom, because that's how the units work out. 26.036. Point 52886 grams. So rounding that would be 0.529 grams of acetylene. Any questions?
So the water partial pressure plus oxygen or
Acetylenes. So we've got two gases here, acetylene and water. And they each have a partial pressure, and those two pressures add up to the total pressure.
738.
738. We can measure the total pressure. If you have a sample with a mixture of gases and you don't know the quantities or the mole fractions or the volume percentages, you can't calculate what the partial pressures are. For water, we know what the partial pressure is because it only changes with the temperature. And so if we know what temperature it is, we can look up the vapor pressure and subtract that out, which is really great because collecting a gas over water is very common. So then you have a wet gas, and you need the pressure of the dry gas. Any other questions? Yes?
The N equals PV over RT, is that one that we are just supposed to remember, or is there a way for them to change
So this one, N equals PV over RT, that is just taking Pivner and rearranging it.
rearrange it out?
Yeah, so up here I've got PV equals nRT if I want to get N by itself. I'm going to divide both sides by what is next to the N. So the R's cancel, the T's cancel. And then if I do it to one side, I have to do it to the other side. Yeah. Any other questions? You guys are waking up a little bit. Which is awesome because, we're almost done. So here's another one. Common way to make hydrogen gas in the laboratory is to place a metal such as zinc in hydrochloric acid. Hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? Alrighty. Well, let's pull out some numbers. 154.4 milliliters. Well, that's the volume, right? Because milliliters is a unit of volume. We have pressure of 742 millimeters of mercury. Now, this is collected over water. Is this going to be pure hydrogen gas? No, it's going to be hydrogen and water vapor. So this is the total pressure. So that gas sample, that wet gas, has a total pressure of 742 millimeters of mercury. And then they tell us that the temperature is 25 degrees Celsius. Is that going to be a good unit for any temperature, gas calculation? No. Convert that to Kelvin. That's 298 Kelvin. So we just used this equation. N equals PV over RT. Rearrangement of PV equals nRT. This is similar to the last problem we did. There we had a mass, we were looking for a mass of acetylene. Now we're looking for a mass of hydrogen, right? So we're looking for a mass. Ideal gas law allows us to calculate moles, and then we can convert to mass, right? So we need to calculate the moles of hydrogen first. Can we use the total pressure to calculate moles of hydrogen? No. We need to find the partial pressure of hydrogen. We need to subtract, so the total pressure equals the pressure of hydrogen plus the pressure of the H2O. So the pressure of hydrogen equals the total pressure minus the pressure of water. But they didn't give us this. What do? We look it up. Don't memorize these. I don't know what they are. The only one I know is that 100 degrees Celsius, the partial pressure of water is 760 millimeters of mercury. You do not memorize these. They will either be given to you in the problem, like in the previous problem, or you would be provided with a table like this. So the temperature is 25 degrees Celsius. We look up on this table, and the vapor pressure of water is 23.78. The pointer's going off by itself there. 23.78. So the partial pressure of the water, 23.78, is that what I was saying? So to find the pressure of the hydrogen, we're going to subtract. Now I don't want to do that one in my head. I did write that down, honestly. It'll catch up with me eventually. 742 minus 23.78 equals 718.22 millimeters of mercury. And the last sig fig would be in the ones place. Finding the partial pressure of a gas, if you know the other partial pressures and you know the total pressure, is just a matter of subtracting. So N equals PV over RT. We do have to convert, right? Because here we have volume in milliliters. So I'm going to move this over. 154.4 milliliters, how many liters is that? 0.1544. So that's our liters. I already converted the temperature. Millimeters of mercury, it's 1 atmosphere for every 760 millimeters of mercury. .940, no, 945, 02 atmospheres. N equals PV over RT. .94502 atmospheres times the volume, 0.1544 liters. Divided by R, 0.08206 liter atmospheres per mole Kelvin, and 298 Kelvin. 0.00596, there's my 3 sig figs, 68 moles. You okay with that? We got moles, we want milligrams. So we're going to do moles to grams to milligrams. So here's our moles, 0.0059668 moles of hydrogen. Okay, formulas weren't given in here at all. We talked about zinc and hydrochloric acid and hydrogen, but they were all the names. What's the formula for hydrogen gas? H2. Hydrogen gas, hydrogen's all by itself, so it's a diatomic element. Is that going to make a difference? Yes, it is. It's going to make a big difference. Because if you had hydrogen atoms or hydrogen molecules, if they're molecules, they take up half as much space because they're paired up. It's like carpooling, right? You got 50 people. If they each drive their own car, that's 50 cars. It's going to take up a lot of space, say in a parking lot. If you carpool 2 people per car, now you've only got 25 cars, it takes up less space. Same thing with the gases. When it's a molecule, you've got the 2 atoms in there taking up the same amount of space in the gas as 1 atom. So it's important to get those formulas correct. So when we calculate the molar mass, we're calculating it for H2. Yeah, that's wrong, isn't it? See what I did there? That's messed up. It's upside down. You go to cancel the units out and you realize, oh, wait a minute. 2.016 grams on the top, moles on the bottom. There we go. And then if I want to go from grams to milligrams, 1 milligram is 1 times 10 to the minus 3rd grams. And the grams cancel out. What am I doing? I don't trust that. 0.0059668 times 2.016 divided by 1 EE minus 3. Yeah, okay. I somehow got sine in there. Like, wait a minute, there's no signs in here. SINE. So that many milligrams. 12.0 milligrams. Any questions? Similar to the previous problem.